Hi everyone, my name is Alexis Segoviano and I will be presenting for Group 1. My team members are Anaí Ramos, Priscila Rodriguez, April Todd, and Aileen Muriel. On this lab, we focused more on Ohm's law and saw how it applies to resistors in series and parallel circuits. The goal of this experiment allowed us to explore the relationship between voltage, current, and resistance and see and test out how resistance changes depending on how resistors are connected. Ohm's law is basically the rule that connects those three things. It says that voltage equals current times resistance, or B equals I times R. Even if we don't think much of it, we use this concept in real life, such as a heater in our house, and it depends on resistance to control how much current flows and how much heat is produced. So we tested individual resistors and then combined them in different ways to see if the total resistance changes or and to see how close our results were to what we expected. So for our materials, the materials that we used in this lab was a voltage current sensor, a passport interference, positive and negative wires, three different types of resistors, and the capstone program, which was the computer, as well a calculator for calculations. These tools allowed us to measure the voltage and current precisely and calculate resistance using the slope of the line on our voltage versus current graphs. So this is just an overview of how we set up our equipment in the different steps of the activities. So for the first one, we use the table provided by the activities lab, and we used the color band code key. So black is 0, brown is 1, red is 2, orange is 3, yellow 4, green 5, blue 6, violet 7, gray 8, and white 9. And for setup 1, we tested out how one resistor um, is connected to the machinery, and then setup 2, we could see it in a parallel form. And setup 3, we could see it both, a combination of both parallel and the series form. So for procedure, we started by connecting the voltage LEDs to the Pascal interference to the circuit, in which both the positive and negative wires were plugged accordingly. For step 2, each of the three resistors were read based on the color bands and labeled resistor 1, 2, and 3, filling in the table with our results. For step 3, the capstone program was launched on the computer and a graph was created in which the y-axis was the voltage and the x-axis was the current. So for step 4, the first resistor, which was 1000 ohms, was connected and the values in the single generator were manually adjusted with the max voltage set to 10V. Together, the date of the preview button was selected and set at 0V and gradually increased by 1V until we reached 10V. Next, the keep button was clicked after each increase and the process was repeated for each of the three resistors, resulting in a graph image, which was taking a picture and recorded. Next, Each of the three graphs had its slope calculated in capstone and was used to fill in the table 4 with the results for resistance and percent error. The second part of the experiment required two different setups with all three resistors. Setup A, which the resistors all lined up in a parallel form, and setup B, which were in a series. For step 9, similar to the first part, the preview button was selected and then set to 0V, and it was increased by 1V until we reached the max of 10V. So same thing, the keep button was clicked after each increase, and the process was repeated for each setup, resulting in a graph for each. The theoretical resistance was calculated in the series and parallel using our experimental values for the resistance using a specific formula as shown above. And based on the data and the slopes calculated in capstone from each of the graphs, the results were used to fill in table 5. The final step consisted of connecting two of the resistors in parallel and one in series, where each of the three resistors got to be in series. And just like the previous steps, the preview button was selected and it was set at 0V and eventually increased by 1V until it reached till 10V. The keep button was also clicked after each increase and the process was repeated for each setup, giving us a graph for each. Each of the three graphs had its slope in capstone and was used to fill in table 6 with the results. So you could see a diagram there for setup A, that's what I meant, the resistors were stacked up against each other, and for setup B, more of a stair form. And the formulas was use those formulas. So for the first graph shown here, it shows the measurements that we got for resistor 1 starting from 0 volts to 10 volts. And then we obtained the resistance amount by finding the slope of the graph. On the table, the resistance amount became our exponential value, while the theoretical came from the color coding bands on the resistor. And for the first resistor, the color did start with brown, so which was 1,000, which is their theoretical value. And for the percent error, we found the 3% error. So we did the same procedure for the next graphs and tables for resistor 1 and 3. And for resistor 2, we found it to be 390, and for resistor 3, it was 56 for a theoretical value. Next, we made a prediction and we thought that setup A, the parallel form, would have a higher resistance overall. And our reasoning for that was that since more resistors were being added and more of as a unit in a way, the total resistance should increase. And this is just a video showing us for setup A and plugging in the values, increasing it from 0V and gradually by 1V until we reach 10V. And always hitting the keep button so our graph could be measured. So the in the formulas, the values that you see there were taken from the experimental values that we got in the graphs. And after calculating those values, we saw that the theoretical resistance for the parallel was 45.03, and for the series was 1,476. So those are our graphs for setup A. And we noticed when we analyzed the data, we found that setup B, the series, actually had a higher total resistance, which was around 104, 1,420. Next, we calculated our percent error between the theoretical and experimental values for the series and parallel. And for the series, we found a percent error of 3.8, in parallel 1.55. So for the last step or activity for the experiment, which was the combination of parallels and series, we looked how changing the value of a single resistor affects the total resistance, and a series circuit increasing one resistor's value increases the total resistance while decreasing it lowers the total resistance. In parallel, we saw that adding more resistors kind of lowered the total resistance because it increases the number of current paths. So here is table 7. In conclusion, this experiment did help us understand how Ohm law works and how the arrangement of resistors and values can affect the total resistance in a circuit. Our data showed that the relationship between voltage and current is linear, and the slope of the graph can be used to accurately calculate resistance. We also learned that resistors in a series always result in a higher total resistance, and that is because the current must pass through each resistor. In contrast to it being a parallel, it lowers the total resistance since the current can be split and taken into multiple paths. In series, the resistors are connected end to end, so there's only one singular path for the current to travel. Like if it was a long road with 3 toll booths in a row. The current has no choice but to go through every resistor end after end, and it adds to the total resistance. So it's harder for the current to flow and it makes the resistance higher. Whereas in a parallel current, all the resistors are connected on the same points on the voltage source, so the current has multiple paths to travel through. Our calculated resistance were mostly due close to the theoretical values, but there were some small percent errors, and that probably came from measurement errors or resistant or imperfect connections. The percent error is an important part to understand and our reliability of our data, and a low percent error means our experimental results closely match the theoretical predictions, showing that our setup and measurements were accurate. Overall, this lab not only reinforced the concept of Ohm's law, but also demonstrated how crucial resistor configuration is in a circuit design. In this experiment, we explored the relationship between voltage, current, and resistance using Ohm's law and applied it to both series and parallel resistor networks. By analyzing the slope given by the voltage and current graphs, we determined that the experimental resistance values and compared them with theoretical ones given by the color band code. And the results demonstrated that resistors connected produced a higher total resistance while those connected in a parallel had a lower overall resistance. here are the credits.